Our next topic is RISC pipeline. We have learned about pipeline, how instruction or an arithmetic operation can be divided into sub operations and can be performed faster using pipelining. So here we are going to learn about RISC pipeline. RISC is reduced instruction set computers. We have learned in the earlier chapters about the two architectures, RISC, reduced instruction set computer, and CISC, RISC and CISC. CISC is complex instruction set computers. Okay, in this RISC architecture, the instructions are simple, and complex architecture, okay, complex instruction set computers. In those computers, the instructions are complex. It takes a lot of time to execute those complex instructions. So here we learn about RISC pipeline, how pipelining is implemented to execute this instructions, those simple instructions in RISC architecture computers. So let's start with the RISC characteristics. The main characteristics, okay, of RISC are instruction pipeline and single cycle instruction execution and compiler support. Okay, one of the characteristics of this reduced instruction set computers is its ability to use an efficient instruction pipeline because of the simplicity of instruction set that can be divided into sub operations. Okay, the simple instruction, RISC computers will have a simple instruction format. These instructions can be broken down into smaller sub operations very easily. Okay, because of this feature, computers can use an efficient pipeline. Okay, so one of the characteristics is its ability to use an efficient instruction pipeline. Okay, so instruction pipeline can be, as we discussed in the last class, instruction pipeline, instructions are divided into sub operations and can be executed parallelly. Okay, here these instructions, as they are very simple, instruction pipeline can be implemented with a few segments, 2 or 3 segments. Okay, and the next characteristic is single cycle instruction execution. Okay, these instructions are of fixed length. The other characteristic of RISC is instructions have fixed length. Okay, and when broken down into sub operations, okay, and executed in 2 or 3 segments, these sub operations can be performed in a single clock cycle. The instruction may be a data transfer instruction, or it may be a data manipulation instruction that performs the manipulation operations on the data, or it may be branch instruction. Correct? The instruction set, okay, of this RISC computers may include a data transfer instruction, data manipulation instruction, or a branch instruction. Data transfer instruction can include the memory reference because the transfer instructions are meant for transferring data from memory to the CPU registers or from the registers to memory. So we have discussed earlier, it may be a load instruction. Okay, load R1, comma A. A is a memory operand and R1 is the register. So here the data is transferred from memory to R1. So this is a memory reference instruction. Here memory access is required. Or it can be the two instructions that can be used for data transfer are load and store. Store instruction transfers data from the register to memory. Okay, that is to store in memory. So if we write it as A, R1, the content of register R1 will be stored into register A. Okay, sorry, memory location A. So data transfer instruction here are limited to only store and load. And data manipulation instruction cannot have memory access. Okay, in this because of this reduced instruction set architecture, the data manipulation instructions cannot have memory reference like addition, Okay, if an instruction add, if there is an instruction add that performs addition of two data elements. Okay, if these data elements are, it can be performed only on register. That need to be, the data need to be transferred to register first. Okay, so the syntax would be R1, R1, R2. It adds the content of R1, registers R1 and R2 and transfer it to R1. Okay, this is an example for a data manipulation instruction in RISC architecture. Correct? Here we can't give add the instructions such as add R1, A. A is a memory operand. Data manipulation instructions only can have registers. They can operate on the data that is stored in registers only. Okay, if the data is already in memory, they need to be transferred to register. Okay, so these are data manipulation instruction. And the other type of instruction can be branch instruction. It can be a branch unconditional instruction or conditional instruction such as branch if carry, branch if zero, branch if not carry, and no carry. Okay, these type of instructions. So here, when we consider the instruction, the instructions would be very simple and can be broken into smaller sub-operations, and each operation can be run in different segments parallelly and executed in a single clock cycle. And the other characteristic of RISC is the support given by the compiler that translates the high-level language program into machine language program. As these instructions, okay, as these instructions are simple, they can be converted into a machine language instruction directly. Every high-level language instruction can be converted to a machine language instruction directly. Also, we have discussed the difficulties that arises during instruction pipelining. Correct? Data dependency, resource conflicts. Okay, at the same time, different instructions trying to access the same device. So that is resource conflict. And data dependency, the instruction that need to work on some data that is not available, that is being processed by the previous instruction, that is not, the data is not available for the current instruction to use, that is data dependency. And branch difficulty. Okay, during branch instruction, there will be a delay in execution of the next instruction. To handle these difficulties, okay, other computers use a special hardware is designed to manage all these. These RISC computers, instead of designing hardware to handle the difficulties, they rely on compiler, okay, to minimize the delays or the difficulties that are encountered, okay, during this pipelining process. So these are the characteristics. And if we consider a 3-segment pipeline, and these instructions, if we classify into 3 sub-operations, and it is run in 3 segments. Okay, so if we consider a 3-segment pipeline, the 3 sub-operations of instruction cycle are, first one is instruction fetch, okay, denoted as I, and second, we combine this decode phase with the ALU operation. Instruction decode and ALU operation are combined to one sub-operation here, that is denoted as A. And third sub-operation is execution, that transfer the output of ALU to a register, or it may be to memory, transferring it to memory, or PC. The first phase is, we are dividing the instruction cycle of this RISC instruction into 3 sub-operations. Okay, those are run in three different segments parallelly. First sub-operation is instruction fetch, I, instruction decode and ALU operation, A, and transfer of output from ALU, okay, from the operation that is performed in ALU to a register, memory, or PC, that is execution phase. Instruction fetch fetches the instruction from memory and, okay, into IR, right, instruction register to memory. This is the first phase. And second phase, decode the instruction. Okay, this phase is to understand the meaning of the operation that need to be performed, and the ALU operation. Here the ALU operation can be the three types of instruction. If the instruction is a data transfer instruction, what is the ALU operation? If the instruction is such as load or store, the ALU need to calculate the effective address. Okay, so finding the effective address of the data, the operand that is in memory. So finding the effective address in case of data transfer instruction. Or if it is data manipulation, such as this, add R1, R1, R2. Okay, so here the operation is adding the content of R1 and register R1 and R2. So the ALU performs the addition here, addition of R1 and R2, and stores it in R1. That is the operation done by the ALU. And in case of branch instruction, okay, if the third type of instruction is branch instruction. So in case of branch instruction, the operation that ALU performs is finding the branch address, right, or the target address, where to branch. Control has to be taken to a different location that is specified by the given in the instruction. If it is branch unconditionally, okay, X is the location where the control has to go to execute the instruction, okay, execute the next instruction. So here calculating this, okay, this is an address, so getting that address, okay, that is the operation performed here. Okay, so these are combined in one phase, instruction decode and ALU operation. And once that is done, execution phase transfer the output of ALU to a register or to memory. Okay, after the operation, manipulation operation, if the data has to be transferred to register, it is to transferring to register, that is execution phase. Okay, or it can be transferred to memory or PC. When the data will be transferred to PC? In case of branch instruction. Correct. If it is branch instruction, ALU operation is calculating the branching address and transferring it to PC, so that the next instruction fetched, okay, will be automatically the instruction that is addressed by this PC. Okay, so these are the sub operations. So here, if we take this example of example of these instructions, load. First instruction is load. Okay, each instruction is divided into 3 sub operations. Okay, so every instruction here, load, we have first instruction as load instruction, load R1, memory at location address 1 to R1. Okay, so this transfers the data from memory location, okay, in the given address 1 to register R1. And second instruction is load R2 with the memory content, okay, memory content at address 2. So this is loaded into R2 when this instruction is executed. And third instruction is add. This adds R1 and R2 and stores the result in R3. So we get the result in R3. This is the third instruction. And fourth instruction is store. Okay, this is to store the result in memory. So the memory result that is in R3 is stored into memory at address 3. So let's take these 4 instructions, okay, for understanding this pipelining. Here, this space-time diagram, okay, that shows the timing relationship between these sub-instructions, sub-operations, okay, that are performed in different segments. So here in the rows, we have the instruction. We have 4 instructions, so there are 4 rows. Load R1 is the first instruction. Load R2 is the second instruction. Add R1, R2 is the third instruction. And store R3 is the fourth instruction. Each instruction is divided into 3 segments, correct? 3 sub-operations. Those are run in 3 different segments. The 3 sub-operations are I, A, and E. I is instruction fetch, and A is decode and ALU operation. E is execution. Okay, and here in the columns, we have clock cycles. So during the first clock cycle, instruction 1 is loaded, means fetched. Okay, so instruction fetch, the sub operation is done. And during clock cycle 2, as these are done in different segments, so this can be done parallelly, okay, executed parallelly. So during clock cycle 2, the instruction 1 will move to the second phase, that is decode and performing ALU operation. At the same time, instruction 2 will be fetched. Okay, second instruction will be fetched from memory into CPU. And during clock cycle 3, the first instruction goes to execution phase, and second instruction is decoded and ALU operation is performed, and the third instruction is fetched. Okay, and during clock cycle 4, this way, every operation is started in the subsequent clock cycles. And here there is a data conflict. Okay, if you observe this here, second instruction, load R2. So what this instruction fetch first phase does, in this instruction is loaded into IR, instruction register. And the second sub operation, okay, what this does is, it decodes the instruction. So it is understood here in A phase, okay, in the second phase, that it is a load operation. Okay, load instruction, that is the first operation done here. And the second part is performing ALU operation. What the ALU does, ALU finds the effective address, because it is load R2, means load the content of memory into register R2. So here there is a job of finding the effective address in memory. So this ALU find the effective address. We know how effective address is calculated. Okay, if it is indirect address, it is effective address need to be calculated. So it is calculated here, and during execution, actually the load happens. Okay, the load of loading of data from memory from the given address to register R2 is done in execution phase. So this third, during fourth clock cycle, this instruction 2 goes to execution phase. So here actually the register R2 will be loaded with the memory content. And the third instruction at this time, okay, during fourth clock cycle, the third instruction performs the ALU operation. So here the third instruction is decoded at this place, and it needs the content of what is the ALU operation performed here. It's adding R1 and R2. Okay, R1 is available because the execution of first instruction is over. So memory operand is loaded into R1 in clock cycle 3. But what about R2? The instruction 3 needs R2 also, which is currently being loaded into R2 from memory, okay, by the second instruction. So these two, there is a data conflict here. Okay, we call it as data dependency conflict. Here this instruction 3 is dependent on the data that is given by instruction 2. So here there is a data dependency, okay, for instruction 3 to perform its operation, the data is not available. Okay, it is being processed by the previous instruction. Okay, so here this diagram shows the pipeline timing with data conflict. How this can be resolved? Okay, here it is the compiler's responsibility. Okay, these RISC architectured computers rely on compilers to handle these conflicts. So what the compiler does, compiler delays the operation. Okay, so here to get the value of R2 in this clock cycle 4 for instruction 3, the operation need to be delayed, right? This instruction, this has to be delayed for 1 clock cycle. Okay, so here if the second phase A is done, the data would be available at this phase. So for 1 clock cycle, it need to be delayed. Okay, so the compiler inserts one useful instruction. Okay, in between the second and third instruction, compiler add some useful instruction that delays the operation of this third instruction by 1 clock cycle. If no useful instruction is identified by the compiler, it just adds a no operation instruction. Okay, so here you see that in the next diagram B, space-time diagram B here. The clock cycle first instruction is finished at time 3, clock cycle 3. And during clock cycle 4, the second instruction will be executed. Correct? Execution of second instruction is done at clock cycle 4. At the same time, we have seen here in the previous case that the third instruction requires the value of R2, which is not available. So the operation of this ALU operation need to be delayed. Okay, so the execution of instruction 3 need to be delayed by 1 clock cycle. So to do that, the compiler try to identify some useful instruction that can be performed, okay, in that time, delaying time. Okay, if there is no useful instruction identified, it adds a no operation instruction. Okay, so here you see the third instruction is a no operation instruction that is loaded, that is fetched from memory. Second phase of decoding is done. So when during decoding, it is found that no operation need to be performed. So it does not perform any operation. Okay, so this sub operations of no operation is finished. So, and the next instruction is add R1 plus R2 that is started at during clock cycle 4. So instruction fetch is done at during clock cycle 4, and here during the 5th cycle ALU needs R2, which is available during clock cycle 4 only. Okay, that is loaded by the earlier instruction, second instruction during clock cycle 4. So in clock cycle 5 it is available. So this can now perform the addition of R1 and R2, and during execution that is transferred to R3. Correct? Okay, it is stored to R3, move to R3. So this way the load is delayed. Okay, loading of R2, this type of load is delayed load. With this, the compiler delays the operation, okay, when there is a data conflict. And the next is delayed branch. Okay, delayed load is for handling the data conflict. Okay, and during branch instruction, we have discussed in the earlier class, yeah, we have seen here that in this table, okay, space time diagram, the third instruction is a branch instruction. So during decode phase of this instruction, it will be known to the computer that it is a branch instruction. The execution of next instruction will not be carried out. The branch address is identified in this, okay, during execution, and that is loaded and executed. Correct? Okay, so here the pipeline is left empty. Okay, no operation is being carried out. There is a branch delay here. Okay, because of this branch instruction. Otherwise, sequentially, one after the other, the instructions will be executed. This branch instruction made a delay in this pipeline. Okay, so that is branch difficulty. To handle that, here in this RISC processors, the compiler redefined the branch instruction. Okay, compiler redefined the branch instructions to avoid the branch difficulties. The compiler for a processor that uses delayed branches is designed to analyze the instructions before and after the branch and rearrange the program sequence by inserting useful instructions in the delay steps. Okay, where there is a branch instruction, we know that there will be a delay. So to avoid the branch delay, the compiler analyzes the set of instructions, okay, before and after the branch, and rearrange the instruction sequence by inserting useful instruction in the delay steps. Where there is a delay, it inserts some useful instruction. If no useful instruction is identified, it inserts no operation instruction. Okay, so no operation will be performed, but delay is handled. So delay, a branch delay can be handled this way. Here is an example in the space-time diagram A here. The first instruction is load. Okay, so it is loaded in 3 steps. It is carried out and increment. Then third is add, fourth instruction is subtract. And here our focus is in the branch instruction here. Okay, so branch to X. So what happens here? During instruction is fetched during 5th clock cycle, and in during 6th clock cycle, instruction is decoded and it is understood that it is branch, correct? And then let's consider that it is a unconditional branch. Okay, the instruction is BUN. It is unconditional branch. So there is anyway branching has to be done. Okay, so in this case, it is identified that it is a branching instruction. Here, compiler inserts a no operation. Okay, so when the branch instruction need to be executed during clock cycle 7 is the execution. So here the branch address would be calculated in the execution phase of branch instruction. Okay, so that is done at clock cycle 7. So clock cycle 8, during clock cycle 8, branch instruction can be executed. Okay, so what will be done in this time? Okay, there will be a delay. So to avoid that, compiler inserts some useful instruction. Okay, here we have seen the first diagram, no operation instructions are inserted. So compiler inserts a no operation instruction that is executed. And again, there are 2 clock cycles, correct? The fetch can be done only during 8th clock cycle. So to delay by 2 cycles, 2 no operation instructions are inserted. And during 8th clock cycle, you see instruction in X. Okay, if the instruction is BUN X, X is a branching address. So instruction in this location X is executed during 8th clock cycle. Okay, it is fetched, decoded, and ALU operation is performed and executed. In diagram B, you see this no operation instructions are replaced with add and subtract. Here instructions are rearranged. Okay, the compiler checks if there is a branch instruction, it rearranges the instructions to avoid the delay. So after load and increment, the 3rd and 4th instruction here, add and subtract, are brought down after branch. Okay, so when the branch instruction is being executed, okay, when it finds the branching address, during that time, we can execute 2 instructions instead of just giving a no operation instruction and wasting the time. Okay, if some useful instruction can be identified and loaded here, moved here, would be helpful, right? Those 2 cycles, clock cycle, can be utilized well. Okay, so the compiler moves those instructions here. So add and subtract. So when the branch instruction, when the branch address is identified, okay, during these phases, instead of delaying, okay, instead of the pipe being empty, add and subtract, these 2 instructions can be executed. And then during, once this is over, once the branch address is known during 5th cycle, the branch instruction, that is the instruction in location X, can be executed during 6th clock cycle. So here at this cycle, target instruction is loaded, fetched, then it is decoded and executed. This is about RISC pipeline. Okay, how pipelining can be implemented in RISC processors. Okay, the computers that use RISC processors. RISC is reduced instruction set computers. Okay, so here the instructions are restricted, okay, to a certain format, and the instructions are very simple. So the instructions can be broken down into smaller sub operations and can be executed in a single clock cycle. As pipelining is implemented here, these sub operations can be run in different segments and executed parallelly, and instruction cycle time would be reduced. So the characteristics are instruction pipeline, single cycle instruction execution, and the compiler support given to these computers. These computers rely on these compilers, okay, to take care of all the difficulties that arise during pipelining, okay, during this parallel processing. So these instructions, the instruction cycle can be divided into 3 sub-operations: instruction fetch, and second phase is instruction decode and ALU operation. And the third is transfer the output of ALU to register or memory or PC. Okay, so here we have taken an example. The 3 sub-operations are run in different segments. It's a 3-segment pipeline. So run in different segments parallelly. And here we have seen the data. There is a data conflict during clock cycle 4. Okay, the data that is required for the third instruction, okay, add R1 plus R2, that is not available at that moment. Okay, that is being processed by the earlier previous instruction. So we call this as data conflict. This data conflict can be taken care by the compiler. Okay, compiler inserts another instruction. Here there is a delay. We need to delay the process of instruction 3. Okay, until the data is available. So to delay, the pipeline need to be emptied, right? Made empty or kept idle. Okay, to avoid that, some useful instruction, compiler look for some useful instruction and it inserts that instruction at that place. If there is no useful instruction found, a no operation instruction is added. So here this diagram B shows the no operation instruction that is being executed during the delay time to avoid the delay. And delayed branch, even during branch, there will be a delay until the branch address or the target address is identified. That is done during execution phase of the branch instruction. So until that is identified, no instruction can be executed. The target instruction can be loaded only after the target address is identified in the branch instruction. So here there is again a delay. Okay, so here also the compiler adds some useful instruction. Okay, so here in figure A, in diagram A, we see no operation instructions. Okay, to avoid the delay and to make the pipeline perform better. Okay, instead of no operation, here also no operation is being done, but just the delay is avoided. So to make the time useful, the instructions are rearranged. The compiler checks for, in case of branch instruction, compiler checks for some useful instruction that can be moved after branch. Okay, so that the delay can be avoided. Okay, so here we see in diagram B, the add and subtract instructions are moved after branch. So during the delay time, these instructions are executed. Once the target address is available during clock cycle 6 and in clock cycle 5, it is available. So during clock cycle 6, the next instruction, the target instruction in location X is loaded and executed. And meanwhile, the execution of add and subtraction are done during the delay time. And we have one small topic here in this chapter. The last topic is array processors. Okay, I think we can finish that also now. Array processor is a processor that performs computations on large arrays of data. Okay, when a computation need to be done on a large array of data. Okay, large set of data. These array processors are used. There are different types of processors. Okay, first we learn about attached array processor. This attached array processor is an auxiliary processor attached to a general purpose computer. So here if you see this diagram, here the general purpose computer is connected to the attached array processor. This array processor is treated as an external device. Okay, so we call it as auxiliary processor. An array of data cannot be processed without having this array processor. The computer will get connected to this attached array processor through the input-output interface. And that is connected to a local memory that can be accessed faster than other memories. From main memory, data is being transferred to local memory. Okay, that gives data to this array processor. So for array of data to be processed at the same time by a set of instruction. Okay, the example, performing addition on a set of data. Operation may be a simple operation or a complex operation, and performing that operation on an array of data. So this array processor having a local memory that translate, like you can consider it a cache memory that transfers the data faster, okay, that operates in the same speed as the speed of the processor. Okay, we use cache memory. Because it is a fastest memory that operates faster. Okay, same as the speed of the processor. Main memory operates lower than the processor. Okay, so we have a local memory that provides data to the processor faster. Okay, so high speed memory. Here it is connected with the main memory transfers data to local memory from which it is given to the array processor that is connected to the general purpose computers. So this way, the general purpose computer using this auxiliary array processor, okay, an external device, external processor, which is connected through input-output interface, the processing of array elements is done. Okay, this is one type of array processing. And the second type is using SIMD array processors. You know SIMD. What is SIMD? We have learned it. It is single instruction, multiple data. Okay, we are talking about array processing, means the array of data, processing of array of data. And the instruction set is single. Okay, we have a single instruction set that process on array of data. Okay, performs operation on array of data. So SIMD array processor, it is a processor that has a single instruction, multiple data organization. Single instruction will work on multiple data, like performing addition, the same operation. Okay, the instruction would be single instruction. Okay, that adds, but the numbers are different. Okay, when an array of numbers are and numbers need to be added using the single instruction. Okay, that organization, the computer that performs that is SIMD. Okay, so here, yeah, it manipulates vector instructions by means of multiple functional units responding to a common instruction. So we have multiple processing elements. Processing element 1, processing element 2, 3, and n elements. Okay, each are connected with local memory units. Okay, from main memory, the data will be transferred to this local memories. Every memory unit, the local memory unit is responsible for providing data to the processing element for processing, because these processing elements are the different segments what we discuss in pipelining. Okay, they operate parallelly. All these processing elements operates parallelly on different sets of data. As here different set of data are needed, we need different local memory units, right, that provide those different sets of data. And here the instruction is single instruction, right? SIMD, single instruction, multiple data. Okay, so for providing multiple data, we have this multiple memory units. And instruction is single instruction that is broadcast by this master control unit to these processing elements. All these processing elements will run the same instruction, will process the same instruction that is sent by this master control unit. So master control unit controls all these processing of single instruction that is processed in different processing elements on multiple data. Array processing is simple. We have learned about the processing, parallel processing. But when array of data need to be processed, the instruction is single. Okay, one set of instruction process on different data. Here, single set of instructions work on different data. Okay, each processing element is connected to the local memory that provides the data for that processing. And all these processing elements work on a single instruction. As all these processing elements need a single instruction, we have a single control unit, master control unit that controls the operations. So with this, we finish this chapter, okay, in 5th unit, and we have one more chapter. And I remember we left one chapter from 3rd unit that also we will finish. We'll start in the next class. Any doubts here from this, what we discussed today, RISC pipeline and array processing?